This is Dr. Cynthia Furse at the University of Utah, and today I'd like to talk about inductors. We're going to talk about what is inductance and how does it relate to the magnetic field and current. We'll explain the effect of different inductor parameters, and finally what it does to a voltage and current in the circuit. An inductor is a passive element that stores energy in the magnetic field. Passive means that whether or not it's connected to a voltage source, it's still an inductor. An inductor is basically a coil of wire. You can just take a wire and wrap it around your pencil, and you have an inductor. When you drive current through it, as shown here, you have the effect of the inductance. The inductance is given in henries, and it's N squared. That's the number of turns, the number of coil, squared, times the magnetic permeability times the area, that's the surface area of this core, divided by the total length, and again it's given in henries. The magnetic permeability is a property of the material of the core. It's given by the magnetic permeability constant times the relative permeability. For air, mu r is 1. The core is generally made out of ferrite or magnetic material, and that's because it increases the total inductance. So ferrite is typically the material that's used in this core. This is how you can tell which direction the magnetic field goes. Take your fingers and wrap them in the direction of current, the fingers of your right hand, and your thumb will show you which direction the magnetic field goes. In this case, wrap your fingers in the direction of the core, and you'll see that the magnetic field comes out of the top, and because magnetic field lines are always closed lines, it comes back in the bottom. The magnetic field for this solenoid inductor is basically donut-shaped. Here's an example of a wire-wound inductor. The core is a non-magnetic ceramic, so it's more or less like air, except that the ceramic holds it together and also dissipates heat. A very thin wire, about as thick as your hair, is wrapped around the ceramic and then attached on either side to electrodes with a resin coating over the top. Here's a multilayer inductor. The electrodes or connections are on either side, and you can see that you can just print a series of loops, and you connect them by vias. Here's an example of a via. Here's another via. A via is where you drill a hole and fill it with solder, and that basically connects two different layers of your multilayer inductor. Here's a thin film inductor made a very similar way, where you have several layers of coils to make the total inductance. Now let's talk about the electrical properties of the inductor. Remember, it's a passive element that stores energy in the magnetic field, and again, here's a solenoid. The voltage is given by the inductance times the derivative of the current. That means that at DC, when there is no change in the inductance, the voltage will be 0. That effectively means that the inductor looks like a short circuit at DC. Here's the equation for the current. It's the integral of the voltage divided by the inductance. And here's the equation for the energy. This is what happens to the inductor. The current basically starts out at 0 and gradually rises to its full total value for current. The total value for current, remember that the inductor would be a short circuit in that case, would simply be V over R in its final state. The voltage, on the other hand, does change quickly. It goes from 0 to all of a sudden going up to a maximum value and then dropping on down. The maximum value of this voltage is the source voltage. So we can see that time t equals 0, the current is 0, and the voltage across the resistor is 0, but the voltage across the inductor is the source voltage. At time equal infinity, or late time, steady state, the current is VB over R, as if the inductor were a short circuit, and the voltage across the resistor goes to VB, whereas the voltage across the inductor would be 0. This is all controlled by a time constant. The time constant for this circuit is L over R. Time constant tells us how quickly the voltage drops or the current rises. So the way this works is current begins to flow in the inductor and it starts to create a magnetic field. At time t equals 0, this acts like an open circuit. The voltage is high and the current is low. But very quickly, as soon as the magnetic field is established, the current flows freely, so at time t equal infinity it acts like a short circuit, where the voltage is low and the current is high. So what does an inductor do in a circuit? Here basically is the equation for the voltage, considering the time constant. This is a picture of the current for this particular example, where we have a 1K resistor and a 1 millihenry inductor. The current rises, reaching 66% of its value at time tau. This is what happens to the voltage. It starts at 0, it jumps up to the source voltage, and at tau it's 36% of its original value. So this is what the inductor does to the voltage and current in the circuit. This is what it would look like if you hit an inductor with a square wave. The voltage would rise and fall, and then when the square wave dropped, it would fall and rise. This is basically acting like a device that gives you the derivative of the voltage that was initially put on the inductor. Inductors in series and parallel. Inductors that are in series add, just like they did if they were resistors, and inductors in parallel add as if they were resistors. So here's how we can use inductors. There are many applications for inductors. Inductive coupling is a very cool thing where you use the current to produce a magnetic field. The magnetic field moves to another coil right here where it is picked up, and a current comes out of this coil. Here's an example of inductive coupling on the University of Utah campus. Wave has created an electric-powered bus. Underneath, there's a coil of wire in the bottom of the wave bus, and then in the concrete underneath is another coil. The current is induced in the coil in the concrete, which is picked up in the coil of the bus in order to charge its batteries at a stop. BlackRock Microsystems has created an inductively coupled brain stimulator where you have 100 electrodes shown right here, very, very small needle electrodes, and this coil right here with a lot of different turns is used to couple to power outside through the skin. Here's a picture of a passive ID chip. This is often used in theft detection devices in commercial sales. Here's a little circuit right there, and here's the inductor that is picking up the current that's picking up the magnetic field from an externally generated source. Here's a picture of the passive ID that's normally used to tag animals, and there's the coil inside. Here's an application of a transformer. On one side, on the primary winding, you'll have a number of windings N1, and they will generate a magnetic field which is going to go through this transformer core as shown here, this donut-shaped thing. And then on the other side, you can have a different number of windings, N2, to pick up the magnetic flux that's going through there. What will happen is you will change the current on this side, and you'll get out actually less current on this side, less voltage, so that you're able to change the voltage across the transformer. Here are several places that you might have seen transformers: up on a power pole, as a charger for your devices, as a taser, or on top of an electric power system. Inductors can be used as both high and low pass filters. Here's a picture of a low pass filter where the inductor is here and we're reading the voltage across the resistor. So what happens? If a DC signal goes through, the inductor acts like a short circuit, and so a large voltage is read across the resistor. But if a high frequency goes through, the inductor acts like an open circuit, and so no voltage makes it through to the resistor. Here's the high pass configuration, and that's just the opposite. So I'm sure you're very curious about where the picture was from the front of from the introductory slide. This is in White Canyon in American Fork.